I just mentioned some things about the final exams briefly before we go to the discussions on the things. So you can see there is no homework 5, 6A, 6, 7A solutions on this test yet, but I have already sent an email to the TA asking him to post the solutions as soon as possible. And if you take a look at the bottom tab, and then you will see the practice final exam. And I will also show you the solutions one by one on Thursday's class. And you will have exactly the same questions on your final exam. Those should be 3 points. If you write down it, and then you will get the points. Other questions would be the similar questions as your homework, and Gaussian elimination algorithm, and whether this system has no solutions, infinite solution, and then there will be some similar questions here: the area factorization, and the Cholesky decompositions, and also the matrix norm, Wheeler norm, and also to verify if this is a Wheeler norm, and also find the norms given by the norms here. So as I mentioned here, all the questions on the exam is from computations. You just need to be familiar with the computation, make good practice, and then prepare for your final exam. And that's super similar for with the how many questions on the exam, right?
What is like?
You will see that they are all the. Yeah, they are. I consider that I don't want you to read the materials before the midterm. It takes a lot of time, right? So you just need to practice some things on the things after the midterm. So you don't need to read the things before the midterm, and that's a good thing. And you will see all these calculations, computation, and it's super easy if it's something similar to what you did in the high school. And as I just asked you as part of the class, and then you prefer to have the proof questions outside the in-class exam. So I will give you the proof questions, just one proof question, but there are 2 small questions there, and then outside the top of the class. And then you can use the internet to help you to finish that proof exam. It's a take-home exam. And you can also discuss with your classmates, but you cannot copy your classmates' homework or your solution, okay? You cannot just copy and paste. And you are not allowed to, for others, you are not allowed to show your solutions to others. You can discuss right on the blackboard and so on and so forth, but you cannot say, this is my solution, and then please copy it. And you cannot do that, okay? You can discuss with your classmate, but you cannot say, okay, I hand this to you, and then you give me a dinner or lunch. This is not allowed. This is not allowed. You cannot sell your solution. It is not allowed. I know this because I was a student. And so there's a proof question, and it could be difficult, but I will also give you the hints, and you can also write down the definitions there. Okay, that's it. And I would like to mention it once again, and then I will talk about the practice exams solutions. And also, there are 2 hours. I would not make the exams to be 3 hours long. It would be very exhausting. So it would take like 6 questions to 7 questions. It's a lot, I know. But you need to make practice a lot, practice again and again on these questions, and then you make yourself familiar with the question, and then you can benefit in 1.5 hours if you make a good practice on this. But if you just try out the practice final exams the day before the final exams, and that doesn't work because you are not familiar with the material. So I suggest you start practicing on the final exam today, and then another day, every other day, and then you go back to this final exams, and then you will get a very good grade on the practice on the final. So that's it. And let's go to the class. Continue our discussions on the materials. So last time we have mentioned some things about the iterative methods, and then today we are going to continue our discussions, and then I get my old iPad back. So this is the good news. I get used to use my old iPad. And let me share you the screen first. Any questions about the final or any suggestions? Make it easy, I know. I would release today, and then when do you think it's a good due day? Suggestions? Next Friday? Yes, okay. Next Friday, okay.
Recording in progress.
How many points, right? I guess it's 10 points. Yeah. So the final exam would be like 100 in total, and then 10 points is take home. Yeah, but you need to do some further extra reading to do that proof. So it's 10 points, but you can get it correct if you discuss with your classmate and do some internet search, and I allow you to do that. Okay, let me just. Okay. The due date is next Friday, right? You decide it, and then you should finish it. And this is the take-home one. And I will write as much as the instructions on the final exams, and then you would know you would know the questions when we talk about the material today, and then you would know that questions. And I just leave that blank, the proof, but you need to finish it. Okay, so let's see what we have. Stop sharing. So let's see what we have learned from the last time. So we do a lot of calculation, and then we just introduce, let me see, we introduced the Jacobi's methods. Actually, let's go back to what we have in the very beginning. At the very beginning, we talk about the vector norms, and then that is something you need to know for your final exams, how to calculate the two vector norms we have, the infinity norm, and then we also introduce the L2 norm for the vectors, and then in your homework, there is a definitions for the one norm. Also, let's see, you need to also memorize the L1 norm definitions. It's homework, but you also need to memorize the definitions there. The matrix norm, they have the corresponding matrix norms, and the infinity norm, the L2 norm, and then the L1 norm. And I want to mention it's very important about the infinity norm and the L1 norm. And let's say we have a matrix look like this, 2, 3, 1, and then 3, 4, 5, 6, 7, 8. And then if it's asking you to get the L infinity norm of this, if it is asking you for the infinity norm for the matrix, and also it asks you about the one norm, and you will see that I show you there's a trick to memorize it, and that's because if you take a look at the infinity sign, and then it's going horizontal, and then if you take a look at the one, and then it's just vertical. So if you want to memorize the definition of the norm, and then for the matrix, and then there's one way to calculate it, right? And then this one, it's just that because it's horizontal, it means row, right? So this is horizontal, and then it means row. We need to compare row by row. And then we need to compare by column, one column by column, because this is horizontal, this is vertical. And this means that we get the sum of the absolute value of the components of the entries in a row, and then take the maximums around the row, among the rows. And because you can see this symbol is horizontal, and this is how I memorize it. You get the sum of the absolute value of the entries in a row, and then we have 3 rows here, and then it means that you are going to do the sum for 3 rows, and then compare all the values we have here, and then take the maximums among the rows. And for the columns, and then you would see this. So it means that we are going to do the similar things, but here we are going to take the sum of the absolute value of the entries in a column, and then take the maximum among all the columns we have here. And let's see. So for this infinity norm, and then you will see, okay, if you take the sum, right, for each row, and then this is the absolute value, sum of the absolute value of the row, and then it means that the first row we have 2 plus 3 plus 1, and then it's just a 6. Remember that these are positive entries, but if there are some negative entries, you need to take the absolute value. Let's say if this is -1, and then it means that we have to add 2 plus 3 plus the absolute value of the -1, and then it should be the same, the 6. And for this one, the second row is the 12, and then this one is the 15, 21, and then if this is infinity norm, and then you get the sum for each row, and then see the maximums among the rows, and then so here the infinity norm for this matrix is 21. It's 21, and so let's say, okay, if we are going to take the one norm, and then you'll see this is vertical, and then we take the column, compare among the columns. So let's say, okay, for the first column, and then what is the sum of the entries here? We have the 2, 3, 6, and then it's just the 2, 3, 6, and then it's just the 11. And then this is the second column. The sum should be 3, 4, 7, and then it's just the 14. And then the last column, and then it should be the -1, absolute value of the -1, and then plus the 5 plus the a, and then that is the 6 plus a is 14 again. But if you take the maximums among all the columns, which means that we pick the maximums among the 11, 14, 14, and then this one, it should be the 14. Any questions about it? Is it easy to memorize it, the norm in this way? Vertical and horizontal. because infinity is horizontal. Okay, so this is something we mentioned before. The first part in this session, the vector norm and matrix norm. And the second part I would like to, so there is something about the, I have already tell you how to define the eigenvalue. And also the eigenvalues is just the AX equals to lambda X. And if you want to calculate the eigenvalue, and then you should solve the characteristics polynomial. The characteristic polynomial is just the determinant of the A minus lambda I. And this is the characteristic polynomial. And then the series of the P lambda, this is the characteristic polynomial, and then the series of the P lambda is just the eigenvalues. And among all the eigenvalues, and then we would take the maximums, and then that's the definitions of the spectral radius. And we would use this today. Spectral radius lambda A, rho A. Rho A is the maximums of the eigenvalue. And we take the absolute value of the lambda and then take the maximum value among them. And that's the spectral radius. And I believe, do we have a questions on the spectral radius on the homework? No. Maybe I will give you one questions on the spectral radius on the public exams as well. And so let's see, we have already talked about one example on this. And then the next things we have talked about in the previous classes is the Jacobi's methods. The Jacobi's methods is quite simple. We take a look at the linear system, and then so for the X, and then we change some values to the current step, and then change some values from the previous steps, and then we make it to the iterative methods. So one thing we can write down is the matrix format. The matrix format looks like this. The Jacobi's methods, JXK, and then equals to TJXK minus 1, and then plus the CJ. And the TJ here, it represents, so first of all, we have already decomposed the matrix into 3 components. And this is the diagonals on the A, and then this is the lower left matrix part of the A, and then this is the upper right matrix part in the A. And so with the help of the decomposition here, we can write out the TJ and CJ. And for the TJ, it is defined in this way. The TJ is the negative D inverse and the L plus U. And the CJ is the D inverse B. So maybe I will update the practice exam today, and I will ask you to write down the matrix format on the exam. And this is a Jacobi's methods, and you would see that we would use the previous steps information to update the current steps. All the information are from the current steps. But last time we have already also mentioned one updated or upgraded methods about the Jacobi's methods. It's the Gauss-Seidel methods. The Gauss-Seidel methods, although we also have matrix form for it, and then you will see in the matrix form that all the informations are coming from the previous steps, but the idea is not just from the previous steps information. We mentioned this. So in the Jacobi's methods, we have the informations x1, x2. This is the entries in the vectors. the components in the vector k minus 1, k minus 1. And then, so in the Jacobi's methods, we are updating the x1k in this way. x2k, that is the current step component. And then we are going to use all the information on the left-hand side to update the x1, x2, xn in the current step vectors. But for the Gauss-Seidel methods, because for the first step, and then we update the x1k with the information here. And then after we update this information, and then we also update the data set here, because we already get the x1k, and then we update this one to the x1k. And we use this updated data set to update the x2k, and then we get the x2k in the second step, and then we also change this number, update this number to the updated value, and then that is the x2k, and then one by one. So you can see while using some updated message information in this Gaussian-Seidel method, you will see a fast convergence and the results, which means that if we want to solve the linear system with the iterative method, and then you would see fast convergence there. We would get the solutions faster. So faster in the iterations. So let's see the Gaussian-Seidel methods matrix format, although you cannot see the updated update procedures in the matrix format because it's a simplified expressions. So in the Gaussian-Seidel methods, you will see this xk equals to the Tg, G represents the Gaussian-Seidel methods, and then xk minus 1. And you would see that they have the same pattern, right? Tg, Cg, Tj, Cj, matrix and vector, matrix and vector here, but the definitions of the matrix and vector here are different. The Tg it represents, so the Tg is calculated in this way. The Tg is the negative d plus L and then inverse U, and then the Cg is the d plus L inverse B. This is how we calculated the matrix format in the Gaussian-Seidel method. And let's see what we have later. So let me see. I will tell you the convergence results later. But here, let's say, let's take a look at one more method first, and then you would get, I'm not going to assign you the homework 9 because you are preparing for other final exams, right? But I would make the SOR methods as one part of the final exams as well. So I'm going to talk about the SOR methods, and then I will talk about the practice problems on Thursday. And okay, so let's take a look at the SOR methods. So the SOR methods is created to get a faster convergence, which means that the get faster convergence, and then there's a theory behind the thing here. So which means that because we have the input B, right? We are going to solve AX equals to B, and then the input B here, not input B, and then we give it an initial gas X0, right? And then there's a system here, iteration system here, right? The question is, does the approximations satisfy the stopping criterion? And then if we loop it and then get 10 loops, and then it satisfies the criterion, satisfy the stopping criterion, and then we can output the results, right? Output the approximations result X. But if we take 100 loops to get to the stopping criterion, and then you will see you need to take more time in the calculation. And So the aim of the SOR mapper is to get a faster iterations, and then you will see we are upgraded the upgraded mappers, Gaussian Seidel mappers from the based on the Jacobus mapper, and then this SOR mapper is based on the Gaussian Seidel mapper. And now let's see. SOR mapper, the name should be the whole name of the SOR. This is the shortcut for successive over relations, relaxations. And let's see the idea how to get a faster convergence. There's theory behind it, and then we will talk about the theory later on in details. So let's see how to create this mapper first. So we create this mapper based on the Gaussian Seidel mappers. So in the Gaussian Seidel mapper and the derivations of the matrix form, there's one step there. And then that step is D plus, so this is the Gaussian Seidel mapper, one step. Gaussian Seidel mapper, and then there's one step there, and then it's just the matrix format, D plus L, and then S xk, and then equals to the minus U xk minus 1 plus B. And so if we want to get a faster convergence, you can decompose the D into some weighted format. And then the D, so we are going to decompose it and then put a weight on the diagonals. Put weights on the D matrix. And then for the D matrix, we decompose it in this way. The D matrix, D equals to the 1 omega D, and then plus the 1 omega over omega D. And the D omega is just a weight that is positive. And then now, if we decompose the D in this way, you can say this is 1 omega and then minus the 1 minus omega divided omega. And it's actually equals to 1, so it equals to a D. So let's decompose this one with the weight, and then you would see this. So 1 omega D, and then subtract the 1 omega D, and then plus D L xk, and then equals to the minus U xk minus 1. And actually, you would see that I just decomposed this one, right? And then I got this, and then I kept the plus L here, and then the right hand side there. And then now let us rearrange everything to make it more looks nicer, and then get a matrix format for the SOR mappers. And so I'm going to rearrange things here, and I would put, let's times both sides by omega, and then we got D subtract the 1 omega D, and then plus the L. And because I times both sides by omega, so there's the omega here, L, xk. And then on the right hand side, I also get negative omega U xk minus 1. And then plus the omega B. And now I'm going to move the things around, and because there's a subtraction on the left hand side, I don't like it, and then I move it to the right hand side, and then I get it D plus the omega L, and then xk. And on the right hand side, I got the 1 omega D, and then subtract the omega U. And let's see. I am also changing I'm also changing some things here. So on the right-hand side here, originally this one is the XK, right? But here I put it into the previous step information instead. So I'm changing some information to the previous step. Change the information to the previous step. And here I got xk minus 1 and plus omega b. And now let's solve for the xk. So you can see, which means that originally we have all the information here is the diagonal part are all from the xk. But now I put a part of the information diagonal, the diagonal times the vectors. I put part of the diagonal to be the previous step information. So now let's go for the xk and then take a look at the matrix format, and that's our SOR methods matrix format. So you will see this one, the D plus omega L is invertible. If you go to take a look at the assumptions, because we have some assumptions on the matrix as well, and this one should be, let's assume that the left-hand side here is invertible, and then we can do the inverse here, and then that is the D plus omega L inverse, and then 1 subtract omega d and subtract the omega u, and then xk minus 1, and then plus. So we are going to do the inverse for both sides. So the vector here, we have the d plus omega l, and then take the inverse b. And this is the SO methods. And then the very important things here, different from the Gaussian Seidel method, is that we put the diagonal information to the part of the diagonal information to the previous step vectors. So let's see if we write it into this pattern, the TJ, CJ, TG, CG part, and then so we have the, because here the weight is very important, so we are going to write it in this way, xk, and then T omega xk minus 1, and then plus the C omega, because all the things is about the weight, how much information we want to put it, the diagonal information, put it into the previous steps. So here, T omega, if you take a look at the expressions here, we calculate it, and then the T omega equals to D plus omega L inverse 1 minus omega D, and then minus omega U, and xk minus 1. And not xk minus 1, because we only need to, this is the shortcut for that expressions, and then we just need to write down the matrix in the in this formula. And then what's the C omega? The C omega is just the omega D plus the omega L inverse B. Any questions here? So if you take a look at this this parameters, right? And then this is the Gaussian Seidel method, and then we haven't changed the information here, right? And if you take a look, if we let the omega d equals to 1, and then what happens? And what is that method? If we take the omega 1, and that is just this is just the Gaussian Seidel methods. We don't change anything. The Gaussian Seidel methods. Seidel methods. Because you will see we are moving 0 part of the d to the right-hand side. So that is the same as the Gantt cycle method when the omega equals to 1. And when the omega equals to, when the omega is bigger than 1, and then we call this one as the, we call this one is the over relaxation methods. And when the omega is smaller than 1, and then that's the under relaxation methods. And also there's a theory behind it, but I would not talk about the proof or the theory behind it. And there's one thing, one necessary conditions for this SOR method to convergence. You can see there's a critical point here, right? And omega equals to 1, and that is the method we are familiar with, and then if it's bigger than 1, it's over relaxation, omega smaller than 1, and it's under relaxation, and there are different names for it, but there's one necessary conditions for the this method to work, to convergence, and that's necessary for the SOR, the necessary conditions for convergence. It's all about the weight. So you can see the SOR methods is all about the weight. Necessary conditions for the SOR method to converge. And there's one condition for the SOR methods to converge. It means that it requires the omega satisfy these conditions. But if the omega satisfy these conditions, it's not enough. It also depends on the A matrix as well. Because the A matrix would decide the T omega and C omega here, and then the T omega is really important. The iterations matrix is very important, and then you will see the importance later. I will talk about the general iterated methods, convergence conditions later, but for this relaxation method, the weight is also important. If you want it to converge, and the omega should satisfy this. The omega should satisfy it's bigger than, it's a positive weight, and then it should also smaller than 2. And people prove this, but we skip the proof here. But if the problem only specifies this, if it can converge, it should satisfy these assumptions here, this criteria here. And this is the method here. Let's see the next things we want to talk about. So before we move on, and then any questions about the derivations? Any questions? The next thing I want to mention is the concrete examples to calculate it. And if we want to write out, so there is matrix format here, and then if we want to calculate the things, and then you can calculate component by component, and then also you can create the matrix and then some matrix modifications here. And if you want to calculate it components by component wise, and then you can do this component wise calculations. So for each component, you can do this for k equals to 0, 1, and so on and so forth. You would do the calculations in below. And below, this is the first iterations. This is the initial guess, and then the first one is the first iterations vector. And if we want to compare the things component-wise, and then, so let's say we have already get the previous steps K information, and then this is our current step vector, and then we want to calculate it with the SOR method. corresponding to that matrix format, we have this component-wise calculation, and it's just the AII. AII is the diagonal component at the II locations. And we use the previous steps information, and then it looks like this, XIK, and then subtract there's a weight. The weight is very important, omega, and then you will see some similar things as we did before. J equals to 1, I minus 1, and Aij, xjk plus 1. And because this is from the Gaussian Seidel method, but only with the weight. And then you will see some similar things as the Gaussian Seidel method. Some information are from the current step, current iterations, but you have already calculated the results. So we use the user information we have already calculated in the previous step, the I-1 steps, and then we have the K plus 1, the information there, the current step information there. So the next thing should be the things after the index I should coming from the, I believe it should be the information from the previous steps, and then divided by the AII. Let me see. This is the component-wise calculations. And let's see, what do we have here? Am I right here, the index? Yes, it's correct, the index. Okay. Let's see, one concrete example. So I'm going to use this component-wise things to calculate the things. Okay. So one example here, we have examples. We have the linear system below AX equals to B, 4x1 plus the 3x2, and then 24, and then 3x1. And then plus 4x2, subtract the x3 equals to 30, and then minus x2 plus the 4x3, and then equals to the 24. And let's take a look at the Gaussian Seidel method first. And also we need to tell the systems how much weight we want to use, and then the initial guess. So our initial guess here for this example, it's just the 111, and then do the transpose because it's a vector here. And then the weight here, we are going to use the 1.25. It's in the range of between the 0 and 2. And let's see. So because this XOR method is updated version of the Gaussian Seidel method, so let's take a look at the Gaussian Seidel method first. So Gaussian Seidel method solution here. So let's see from the first. So Gaussian Seidel methods. Let's see. So the Jacobi methods, and then we go to the Gaussian Seidel methods, right? And then from the Gaussian Seidel method, and then we go to the SOR method. So let's see. Jacobi methods is just so for the x1, x2, x3 from these equations one by one, right? And so let's see. If we go for the x1 in the first equation, and then we got x1 equals to the t4, and then subtract the 3x2, right? And then divided by the 4. Divided by the 4, and then you will see this is the 0.75x2, and then plus 6. And then from the second equation, so you will get the, it should be, we simple the x2 from the second equation, and then we got, okay, we got 30, and then subtract the 3x1, and then, let me see, so plus the x3, and then divide the coefficients over there, and then we got, it should be the subtract 7 by x1 plus the 2 x3, and then plus the 7 5. point 5. And this is the solutions from the Jacobi's from the second equation. And let's say the x3, we put x3 from the third equation, and then we on the right hand side we got the negative 24, right? And then we also move the x2 to the right hand side, and then divide the coefficients we have for the x3, and then we got 0.025 x2, and then minus 6. Okay, this is just the solution, and then for the Jacobian methods, and then we will naturally put the things on the right hand side to the k minus 1 step, and then this is the current step, and then put it to the k. For the Gaussian cycle methods, so we need to be very careful for the Gaussian cycle methods. For this one, okay, all the things on the left hand side are k. Okay, here, right? On the way here. And then for the right hand side, the same thing before the index 1 should be the k. And then the thing is after or equals to index 1, and then it should be the k minus 1. So here it should be the k minus 1, the x2. And then, so the index before the 2, it should be the x1. The x1 should be the k. This one is the k minus 1. And this is the Gaussian cycle method. This one is should be a k. So this one is the Gaussian cycle method. And the Gaussian cycle method, and then we want to upgrade this one to the this one to the versions we have, and it's the x1. So if we want to get the SO methods, and then we need is we have here. We have put the weight here, but it's not. Let's compare what we have in the Gaussian cycle equations. It's not quite obvious that how to compute here. So I think there's something wrong in the index. Let me double check. It should be I plus 1. I believe this one. It is the idea, but we cannot write down the. It's not obvious to how to write down the. It's not obvious to write down the SOR method from the Gaussian method. But let's see if we do it one by one here. So there's a formula here, right? And then let's calculate the things one by one. So let's say, okay, this is the x1k. X1k here. And we want to compute the first component. It should be the AII, and then what is the AII in this equation? The AII is just the, so 4 here, and then 4 here, and then the 4 here, they are the AII. And then so if we want to use, so this is the first equation, let me just copy down the first equation and then to calculate the first equation in the SOR method. And then so we have the AII, it should be 4. And 4 from the x1k, x1k is just the x1k minus 1. And something, this is the index here, this is the current step, and this is the current step. So I just moved one index forward. We have the x1k minus 1 here, and then subtract the omega. Omega is 125, and then sigma sum j equals to 1 to the I minus 1. So we don't have anything here because the I minus 1 is just the 1, because this is the index, right? And then if I minus 1, and then it's just a 0, so we don't have anything from this equation. And then for the next time we have is and they are the previous step. And then that should be the xj, x1, x2, aij is 4, and then plus this from x2. And then it should be coming from the k. Okay. And minus the bi. The bi is just the 24. Does it make sense? So now what do we have? It's a k minus 1, sorry, because I'm moving the index forward, right? K minus 1. And now what do we have for the k minus 1? And by all things here, and then we got a 0.02 x1 k minus 1. And then for the x2 k minus 1, we got, if you calculate the things, and then it should be that 0.9375, and then x2 k minus 1. And it is just 1.225 and 3 divided by 4. And then for the last time, it should be the constant time, and then it's just the 100 divided by 4, and then times the 1.25, and that is just 7.5. Does that make sense? So here you will see I am subtracting all the equations here because this is the first component, and then there is nothing adding for here for the first step. And it's hard to write the SOR just from the Gaussian methods in the calculation. So I'm going to use the formula instead. So let's see, this is the first iteration, the iterations for the component 1, and then let's say the component 2, and then we would do the same things. And I'm going to copy the second equation here. The second equation here, we got this. And then I'm going to use the formula above, and then for x2k, and then I got, okay, so I got, it should be 4x2. So I'm going to change all the index here. It should be the k, and then the current step, and then this one is should be the k minus 1, and then this one is the k. I just append the examples to my current, the formula to my current expressions. It should be from the previous step. So here it should be the 4x2k minus 1, because this is the diagonal entry, but it should be coming from the previous step. So this is 4x2k minus 1, and then for the denominator I have 4, and then for the omega it is defined in the question 1.25. And let's see. So before the two index. So this part is the things before the index 2, and then so j equals to 1, and then sum up to 2 minus 1. The index should be the j equals to 1 to the 1. So there's just one item from the current step information. So what is the aij? The aij xj here, and then from the k, it should be the 3x1k. 3x1k, and then plus, and then the things after the index 1, it should be coming from the previous step. So 4x2k subtract 1, and then subtract the x3k minus 1, and then subtract the 30, and then that's it. And you would see this. So you would see from all the things here, and then you would see what we did here. We did this. We just did this. So inside the parentheses is you can change the equations to this format: 4x1 plus the 3x2 subtract the 24, right? And this is the things inside the parentheses. But we put the things before the index 1 to be to be the current step information, and then put the things after or equals to index 1 to the k minus 1. And then that's the same thing happen to the second equation. We write this equations into 3x1 plus the 4x2 minus x3, and then put the bi to the left-hand side, and then that is 30. And here the index is 2, right? And then so the things before the 2, and then we put it to the subscript. The superscript is the k, is the current step. And then the things after it, after or equals to the index 2, and then we put a k minus 1 here. And that's the things inside the parentheses. Does that make sense? Any questions? So here you just follow the formula. It's easier to just get the expressions directly from the formula, the component-wise formula, if you want to calculate in your examples. And then by doing all the calculation here, combining all the terms here, and then you will find out that this one should be subtract the 9375x1k, and then 0.25x2k minus 1, and then plus the 3.25x3k minus 1, and then plus the 9375. So you will see I will take a lot of time to compute the value here. And I will also do the same thing for the third formula, the third equations. What is the third equation? The third equations we have here is this. And now let's do the same things. We have x2 minus x4, 3, and then plus 24. And then this one, it should be inside the parentheses text leading by the omega, the weight. So x3k, it should be the AII. AII is just the 4x3. And then this one, it should be with the superscript, is the previous step. And then divided by the 4 is the AII. And then subtract the omega. And then now, inside the parentheses, we just need to put it here. And then before the index 3, and then all the things should be coming from the parent step. So, and it should be before the 3, it should be coming from the previous current step. But if the index is the 3 or later than the 3, and then we should put it into the k minus 1. So here it should be 4x3. This would be the plus side. 4x3, and then this one, it should be the k minus 1, and then plus the 24. So you need to be very careful here. The index here is starting from the I. So now we have the index 3 there. So this one, it should be also from the previous step. It should be from the previous step. It's not the current step. And that's it. And then you do the calculation, and then we got the formula for how to update the third component here with the information we got. x2k, and then subtract the 0.25x3k minus 1, and then minus the 7.5. And that's the thing. This is how we update the component 1, 2, 3. And then I will skip the iteration here. And then you already get the initial solution here, initial gas. And then you will put this initial gas into that formula we have here. And then you can use the calculator or computer to do the calculations. And we just put the initial gas into the updated formula, the update formulas, how to update it, the updating rule here, and then to update the x1 vector, x2 vector, x3 vector. And I would just show you the result here. Let me do this. What's happening? So in our textbooks, on the lecture notes, we got this. So I'm going to show you this. You will see we have already worked out the Gaussian Seidel method and then the SOR methods updating rules in this examples. Let's see. So for the first one, it should be the Gaussian Seidel method, and then this one it should be the SOR method. And this one it should be. Let me see. This one is the K here is the iterations number, and then X1, X2, X3, this is the corresponding component there. And the true solutions, I also want to tell you the true solutions in this example. The true solutions lecture note is posted, so you can take a look at the lecture notes. The true solution is the 3, 4, -5, and then take the transpose. And you would see that the Gaussian Seidel methods. So which one should be the? So this one should be the Gaussian Seidel method. Table 373. Let me see which one is the Gaussian Seidel. I believe this one is the SOR method, and then this one is the Gaussian Seidel method. And what is the stopping criterion there? The examples hasn't mentioned the stopping criterion. So there's a stopping criterion here. It should be the accuracy. Okay, the stopping criterion here, it should be the 10 -7. And then which means that if you test the stopping criterion there, the stopping criterion is the xk, and then subtract the xk -1 norm, and then take the infinity norm, and then divide it by the xk norm. And this relative average or relative difference here is smaller than the 10 -7, and then we can stop. And if you do the iterations in your computer, and then you take a look at the steps you need to stop the iteration, and then for the Gaussian Seidel method, it requires the 34 iterations, and then for the SOR method, it only takes them to stop the iterations to satisfy the stopping criteria. And in this numerical examples, and then you would see that the SOR methods would give you a faster convergence than the Gaussian Seidel methods. But this is just from the numerical way, and then do the experiment, and then you know there's a faster convergence here. You would get a satisfied, what is the convergence, faster convergence? It means that you would get the satisfied approximations to that solutions with fewer iterations, and that is the faster convergence. And so now, this is just the numerical methods to numerical examples to test the convergence results. And next, I'm going to introduce when does the iterations methods converge, and then when it doesn't work. So it comes back to the general iterations method, and then take a look at the general iteration method, and then take a look at the convergence conditions. When will we have convergence result? Convergence results. And as you can see, the general convergence, general iterations methods we have here, it looks like this. So we have the updated vectors on the left-hand side, and then we have the iterations matrix. And it could be the TJ Jacobi method, it could be the Gaussian method, it could be the SOR method, or other upgraded methods we haven't mentioned in the class. But on the right-hand side, that is the information from the previous step, and then press the vector C, the constant vector C. And where we can have this is the updating rules for the k equals to 1, 2, 3, and so on and so forth, with the initial guess x0. And I am going to tell you one theorem about the convergence results about the iteration method, and that is the theorem below. So theorems for any initial guess in the N, because we are working on the N by N linear systems, the sequence, because with this generating rule here, and then we can generate the x1, x2, x3, xk vector. So there's a sequence here. There's a sequence of vector here, sequence of vector here, xk, and then k equals to 0, and then infinity, and then defined by this rule, this iterations mapper rule. And then for each k bigger than or equals to 1, if this is the iterations mapper, and then it has the updating rule looks like this, and it would converges to the unique solution, because we say this sequence is convergent, right? And if this one is converged to unique solution, and this one is converged to x, and this one also would converge to x, the right hand side. So it would converge to the unique solutions, x equals to the tx plus c, and that's one requirement for this updating rule, and then that's very important. And it's all about the updating matrix there, the multiplications matrix there. If and only if the rho t smaller than 1, and then this rho t, I just mentioned in the very beginning of the class, rho t is the spectral radius of the matrix. So let's see one example here. And the example is telling you how to judge to decide whether this iteration method works. So there's one example here. So if you have calculated the T matrix, maybe it's the TJ, maybe it's the TG, the Jacobian or the Gaussian side or SOR method, and maybe you get this. Maybe you would get this T matrix. The T matrix looks like this: 2, 0, 0, and then 1, 1, 2, 1, negative 1, 4. And you will get this matrix, and then it doesn't matter what C vector you have. It only matters, the things only matters is the T matrix. And we have already calculated this, the rho T. And we have already calculated the spectral radius in the previous class, and then we get the spectral radius of this is equals to 3. So could you tell me that if we have an iterations method with the T matrix, look at this. Does the method converge with the theorems above? So the spectral radius is equal to 3. No. Why? Because we require the spectral radius to be smaller than 1. So, but here, your iterations matrix, after the calculation, and then you get the iterations matrix, it looks like this, and then the spectral radius is bigger than 1. And so, hence, the iterated methods doesn't converge. Does not converge. And this is the convergence things about the how to decide whether this iterations methods converge for the iterations methods. So this is the theorem here, and then let's see. There's one corollary, and then that's the final exam proof part. But I will not show you the proof here. the corollary, and then it's all about the convergence rate. Convergence rate, because we can see the SOR method has a better convergence, faster convergence result in the numerical example. But why? And this is the theorem about it. And if you calculate some the norm related to the T matrix in the SOR method, and then the norm of the T matrix in the Gaussian-Seidel method, and then you would see the T norm of the Gaussian-Seidel method is larger than the SOR method. So let's see this one. So if this norm could be any norm, it could be the infinity norm of the matrix, it could be the L1 norm, and it could be the L2 norm. And it could be any norm matrix, and then smaller than 1, and the C is a given measure. And then we have the sequence. So this sequence is defined by the iteration through xk and then tk minus 1, txk minus 1. And this is the iteration through here, plus C, and then converge. And this is because if you take a look at the norm here, and then you will see there's one thing about the natural matrix norm, and then this natural matrix norm, it could be smaller than the rho, is bigger than the rho T. And then so if this one, the norm is smaller than 1, and then your rho T is smaller than 1, so it will converge. So this is the first part of this actions, this corollary, and then it doesn't matter the initial guess for any initial guess you have in the n-dimensional space, and then for any initial guess, and then this updating rules would converge to a vector x. And then the next part, this vector will satisfy the x equals to tx plus c. And it has the following convergence result. Convergence result. So the first one, it is x minus the xk, and this norm is related to the P norm, the matrix norm. So we already introduced the vector norm, and then we can introduce the matrix norm with the vector norm. So this vector norm should be related to that matrix norm. So if this is L infinity norm for the matrix, and then this should be the L infinity norm for the vector, it should be paired. So it's smaller than the matrix norm, and then times the k to the power of k, and then x0 minus the x. So which means that in the k iteration, the error is bounded by the initial error, looks like this, and then with the convergence rate here. Does that make sense? So this one is a true solution, and this is the initial guess. And this is the k iterations result, and then this is true solution. So which means that this error in the k iteration is bounded by the initial error, and then with this convergence rate. And because the norm of the t is smaller than 1, and then you would say this is convergence to 0. Does that make sense? If the k is increasing to infinity, and this is going to 0. So you would see the error is becoming to 0 if you take the k to the infinity. And the next theorem, the corollary, is the error estimate, the convergence result also, and then is the tk, and then 1, and then divided by the t norm here, and then x1, subtract the x0. So which means that because a lot of times we want to estimate the iterations error here, allocate iterations error here. But you don't know the true solution. This is the priori, we call it the priori estimate, but you never get this estimate in real life because you don't know the true solutions, right? So you can estimate the error with the first iteration result and the initial guess. And then this is specified this one. And then the convergence rate here is inside it. Does it make sense? So this is the result, and you need to prove it. It's difficult, but I will give you as much as questions you need. But you just need to prove this too, and then you don't need to prove why it is convergent. Because I have already told you this is the result this, and then because the three of them are first, and then we have the convergence. You don't need to prove this part. You just need to prove the convergence result part. Does that make sense? And then I will give you a similar proof in the assignment file. There's a similar proof as this, similar to this, and then you can take a look at the proof there, and then write down the proof for this one. And that's it. All the things. That's it. And then I would tell you the solutions of the practice final exam on Thursday.